A ranker that only exploits clicks gets stuck. Contextual bandits add controlled exploration, so search can learn without wrecking results. You'll see how to connect the pieces into a workflow that learns from clicks and explores safer ranked results. I'm Professor Pi, teaching Search and IR with simple Python. Bandit Learning to Rank is a way to teach a search system from user clicks while still trying new things. In vanilla click training, the system only shows what it already likes, and a single bad impression can drown out a relevant document forever. The Bandit idea balances two goals. One goal is to serve good results now. The other goal is to try a little safely, so the system can discover better options. Intuitively, imagine you run a small search index for product pages. You want more clicks, but you also want to learn whether less seen items are actually good. Bandit Learning to Rank gives a disciplined way to insert exploration into ranked outputs. The strength is faster discovery with limited risk. The weakness is you must choose how much risk to accept and how to measure the benefit. We will build a small, clear loop that starts with an exploit-only baseline, then adds epsilon exploration, then models position bias, then switches to a confidence-driven UCB score, and finally wraps a safety gate that uses an offline base score to limit risk. You will see how clicks move the estimates, and how different exploration rules change what users see. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. The first snippet shows a minimal ranker built from logged clicks and that baseline. This snippet turns a few logged clicks into a minimal exploit-only ranker. The practical result is a policy that always picks the document with the highest observed click rate. So BM25 and rarely seen items have almost no chance to come back after a bad impression. CTR computes the empirical click rate per document and best picks the item with the largest observed rate. It's intentionally tiny, but it mirrors the feedback loop in click-trained search systems. The visible output shows which document the baseline would put first, which makes the exploitation bias concrete before we add any exploration. We need a simple way to escape that trap without throwing quality out the window. The next change will add a controlled randomness that still prefers high CTR items. This example adds a controlled escape hatch from pure exploitation. The code gives us EPS, the probability of taking an exploratory action, while the non-exploration branch still follows the CTR ordering from before. Because RNG is seeded, the tutorial output is stable, but still shows when the policy chooses to explore. Turn up EPS to probe unknowns more often, but expect more uncertain items to surface. The visible output demonstrates an exploration decision and shows BM25 landing in the top slot this run. Exploration needs feedback that accounts for position bias. If something is shown at slot 1, it is far more likely to be clicked than when shown at slot 2. The loop must convert slates into realistic observations. This code closes the online learning loop after a slate is displayed. The practical point is that clicks are noisy signals because position affects examination, so exam models higher observation probability for earlier slots. New converts the shown slate into observed binary clicks under that exam model. Then the loop appends those clicks back into clicks and recomputes CTR. The deterministic click rule here is a compact stand-in for a real user model. The visible output shows which shown document received feedback and confirms that the CTR estimates updated in the same data structure the ranker uses. Epsilon exploration works, but it treats every unknown the same. A smarter approach is to favor items where uncertainty itself suggests potential. That is where UCB-style bonuses help. This snippet replaces blind randomization with uncertainty-aware ranking. The code keeps the empirical CTR and adds a UCB confidence bonus that grows when a document has fewer observations, so items can move up either because they look promising or because they're still uncertain. Compared with epsilon-greedy, UCB bakes exploration pressure into the score instead of flipping a separate coin. The visible output shows the current UCB winner and the exploration bonus that influenced that choice. Even UCB can expose weak items too often if you have no offline sense of baseline quality. A practical safeguard is to combine the learned signal with an offline base rank and limit exposure for low-scoring candidates. This example combines exploration with a simple safety gate for a complete mini baseline. Base acts like an offline ranker score, and pool normally excludes documents below the threshold while still allowing a periodic audit slot every third step. Inside the loop, means captures learned click rates, score adds the UCB bonus, and HIST receives the observed feedback. Raising the safety threshold cuts exposure to weak candidates, but slows discovery. Lowering it explores faster at higher user-facing risk. The visible output shows total clicks collected and which document the loop learned to prefer. Mapping this toy loop to a real deployment is straightforward. Replace the small synthetic corpus with your search corpus, use your production ranking score for base, track impressions and clicks in a persistent store, and tune the UCB constant and safety threshold while running offline A/B checks. In short, Bandit Learning to Rank is an online way to learn from clicks while keeping user experience acceptable. Use it when you need to discover relevance not covered by logs, and when you can tolerate small, measured exploration. Watch the safety threshold, because it trades user risk for discovery speed. A useful next step is to tune the safety threshold and the UCB exploration constant on a held-out simulation of your traffic. Or run the same code against a specific dataset like the public product catalog you use in development to see how quickly the loop finds better items. If short practical IR helps, subscribe and watch the IR videos.